All right, we've got ourselves our hydrologically correct DEM. Now let's go do something with it. First off, what we're going to do is we're going to identify the location of streams. How to do that is we're going to run what we call a flow accumulation. So essentially what we're doing here is with the GIS is we're not looking at aerial photography, identifying where water is located, satellite imagery, or anything like that. We're essentially using math and basic simple ideas here to identify where different streams are located, where they flow into each other, and essentially then from there, what we're going to do is we're going to be able to draw the location of streams, rivers, and creeks in our Marion County DEM. So here's the operation in terms of geoprocessing tool. What it tells us is it says it creates a raster of accumulated flow into each cell. A weight factor can be optionally applied, and we'll talk about that as well. So what we have here is we have our input grid is our flow direction, of course, from our hydrologically correct DEM. And so we see once again the direction coding, but also the arrows help us to see that we have a general pattern here in which things are flowing this general direction to, looks like this particular location here. In terms of the output, when we run a flow accumulation, this is the output. Notice we have a 6 by 6 raster grid. So what that means is we have 36 cells. We'll keep that in mind. So what this shows is, once again, as it says, it counts the total number of cells that contribute to flow into a given cell. So we'll just go ahead and choose this random cell right here, 3. Where does that number come from? Well, it comes from the fact that we have 1, 2, 3 cells that contribute or bring flow into that particular cell. And so this is a cumulative number in which it continues to add. And so you can see here in which we eventually get to 35. Once again, I said there's 36. So in this case, we have one pour point, POUR, or one output or outflow, let's say. And so essentially what's happening here is the accumulation is going off the grid, and it's going off the grid at this particular cell, which we already identified over here. So essentially what we got is the output cells with a high flow accumulation like 20, 24, 35 indicate concentration of flow over the surface. And so what we can do is then we can use that to estimate the location of our stream channels. The output cells with flow accumulation of 0 are local topographic highs. So think of those as sources or areas that contribute to the flow. Finally, if we're just thinking about this, okay, where in this particular grid would I say there are streams? In terms of running a formula, I would say, you know what, where there are streams in this particular grid are any cells that have a value in the flow accumulation grid above 7. And that means that these cells then, 7, 20, 24, 35, these would then be drawn as the stream network. And so this is a very simple, crude way. Of course, the raster grid that we're dealing with is much bigger than this, but it's a very simple way to show this idea that I'm going to talk about called threshold. Here's another way to interpret a flow accumulation grid. We've got our input, our DEM. So this kind of helps us to get an idea. We have a high area over here, another high area over there. And so in this case, white means high elevation, dark means low elevation. So we have a valley coming through here, and it looks like we have a separation. We've kind of have a higher value. So we have a kind of a topographic feature here within the valley. But we have lower elevation. It looks like that's the lowest value, 1. That we'll see anywhere on this grid, and 3 is also quite low. So then there's the flow direction grid. The arrows help to show the general pattern, and we can see that things are flowing towards 1, and it looks like things are flowing towards the 3, and we've got that separation happening here. Once again, from that cell that's at a higher value, and so we got things going this way, so we got divergence, let's say, at this particular area of the grid. Now we go to the flow accumulation. What we have here is we got 10 by 10. There's a hidden one over here. So we have a 10 by 10 grid. So we have 100. And so we see the largest accumulation occurs over here in the south central edge of the grid. You see the value of 63. So we see that's the largest accumulation. I've got another point of high accumulation over here in the middle over here on the western side. We have some that have the values of 0. And so once again, those are cells that are uphill. They're peaks, ridges, places that create flow, but don't have really accumulation of flow. Now, if we add up the two numbers here, 63 plus 35, that's 98. And so essentially what that means, 100 minus 98 is 2. So these two cells are our outflow points or our pour points in which we see flow leaving the grid, and this way going in that particular direction, and then this way going here. But once again, if I was doing threshold, If I was wanting to identify the stream network in this particular grid, I would say, you know what, I want to find a particular stream network. I want all cells that are above, let's say, 19 to be identified as being part of a stream network. And so essentially what I could do is then it would remove all the other ones, and it would only leave just this cell, that cell, that cell, that cell, that cell, that cell, but we've got ourselves a stream. In fact, 2 of them. Here's our flow accumulation pane, and so here's how we'll input the information. We've got our flow direction grid, and this is our updated one, in which we have our hydrologically correct DEM that produced the flow direction grid. We have our output accumulation raster. You can call it whatever you want, but flow accumulation.img. We have this particular input weight raster. Let's go ahead and talk about that now. So what we have over here is we have a weight grid. What that says is this is kind of, let's do an example. This is a major rain event. So we had a major rain event. This is the same grid. So the same one, continue to use the same DEM, same pattern, all that we've used before. And what we're going to do is we're going to compare the weighted grid, flow accumulation grid, to the one we just produced. The rain, though, it was only over here on the northern slopes, up here in this particular area of the grid. Meanwhile, the southern area, they didn't get much rain at all. And so when we can kind of model or kind of predict flow, we can now add another element and think about it in terms of rainfall, amount of rainfall in terms of this particular type of weighting. And even further, what's this say in the previous example? We assumed that rainfall was happening evenly across every cell. In this case, we're saying it's obviously there just in those upper cells. So the rainfall wasn't uniformly distributed. Now we look at our values over here. We can see the numbers here, 46 and 52. And so the numbers are much closer. And that sort of makes sense. If we think about, we add a weight to this, we add a value to this particular flow direction grid, we think about all this northern slope, it's going to go immediately to this particular pour point. Where over here, it's got to go all the way through here. Further, this particular pour point serves much of this area right through here where they didn't get much rain at all. And so what this does is if we compare it to our previous grid, we can see clear patterns in terms of when we add the weight, how this changed our flow accumulation grid. In fact, it was almost double previously compared to the other one. Now, I mean, they're almost even in terms of the flow accumulation. So back to our flow accumulation pane, went ahead and just ran it as is, and here was the result. And so at first you're thinking, well, I can't really see much there. Well, that's the idea here. Is keep in mind this is a raster in which the stream networks are at 1 pixel. So you zoom in all the way in, and you're only going to see the stream networks as far as their width being 1 pixel wide. And so that's why at first you might not be able to see anything, but if you play around with the grid, if you kind of do some things in the symbology, you can see it much easier. You can also zoom in. In this case, I zoomed in right around IUPUI's campus, and you can see the very, very thin lines. That is a flow accumulation grid. But nonetheless, what we just did here is the flow accumulation grid. When we ran it, it definitely did a good job of showing the confluence here of the White River with the Fall Creek canal here that comes through here just on the north and western edge of our beloved campus. We also have a flow accumulation here, kind of a ditch, and then we have some underwater, some drainage patterns regarding along the road here, and it continues on. So we have some that aren't visible, but those still show up in the flow accumulation grid. So this is fantastic. Now we have the flow accumulation grid, which essentially is identify where we have stream networks. And so now what we can do is we can take those stream networks and then we can then convert them from a raster to something that we can do a little bit more with in terms of the vector data model. And I'll get to that here in a minute. But first off, we got to do something. First off, we have to do what I talked about earlier regarding that threshold. We have to decide, okay, where do we stop? Where do we decide, okay, what streams do we not count? Because the flow accumulation grid, as we just shown here beforehand, it produces kind of some of this stuff that, we really don't need that. So we want only the ones where we're getting a good amount of flow accumulation. We don't want ones that just have a little bit of flow accumulation, because we really want to identify the stream network in this particular operation here. And so what we do is kind of a guess and check. So this is something in which you kind of go out, maybe some field work would help out, going back and looking at some aerial photographs. But all I did here was I went upstream. So I went upstream from IUPUI's campus, kind of followed the Fall Creek all the way up, and I got to kind of about as upslope as I could get up there around Lawrence Township in the extreme northeastern part of Marion County. I also changed the color scheme, and so I changed the color scheme of the flow accumulation grid to one in which it showed cooler locations with lower values and warmer locations with higher values. And of course, what we're looking for is we're looking for high values, because the high values indicate we have a good amount of cells in which they're accumulating, they're contributing to flow into a particular cell. Look at the number here. We got 2.9 million here in this particular example. So what I did was I just clicked on a particular pixel. And so I just clicked on this pixel where we have a little bit of a confluence here of two streams. And so I clicked on that. And so this value was 2.9 million. 2921888. And so essentially what I did was, okay, that's my threshold. So what I want is I want all values that are above that number to be included in my stream grid. Anything lower than that number, I don't want. I want it to essentially be null. I want it to be absent from my stream grid. So to do that, you got to go to the raster calculator. There's a few different ways to do this, but here's how I did it. And so I go to the raster calculator, and so I use the set null statement. So we already did that beforehand in a previous example in this video series. And so we're doing the same idea here. But now what we're doing is we're saying, okay, the flow accumulation grid, which is that flowaccumulation.img. What I want is I want all values that are less than 292188888 to be set to null. So I want them essentially to be clear. I don't want them to be zero. I don't want them to have a certain value. I just want them to be non-existent. However, all values greater than that 2.9 million number, which once again, it's the same number, just copied and pasted into the formula. All of those values that are greater are going to be set to 1. And so then the output, we'll call that streams, and the output was this. And so once again, it's kind of hard to see. Yeah, that's okay, but that's, once again, we're dealing with things that are 1 pixel wide. We haven't messed with the symbology yet. And so what I did was, okay, you can kind of look at it if you can see it. I don't know how this is going to show on the YouTubes, but you can see before and after. And so it's kind of faint, but you can see what we did was we reduced a lot of these streams. And so we only are counting the ones where we have major amounts of flow accumulation, high values of flow accumulation. Those are going to be the areas in which we're going to really stand out and really going to show streams and rivers. We're actually going to see them in reality, let's say. And so what we can do is we can zoom in. And so what I did was I zoomed into a particular one over just south of Speedway where we have Automobile Graveyard. So here is the stream flow, and it kind of falls along here, this particular pattern here. It's kind of hard to see underneath the vegetation. So what we can do is we convert this to a vector, but before we do that, let's do something called a stream order. And so what we're going to do is we're going to convert this particular stream network and denote it based on its stream order. And there's two different methods which are used. And so a stream order over here called the Strahler method. And so the idea here is when we have two streams coming together, and they're what we call first order streams, so they're way upstream. When we have two streams coming together, they then create a new one, and we call that 2. And so anytime you get two of the like ones coming together, we then increase the number of the next order. And so we have a 2 and a 1 coming together. Once again, if we have the like ones coming together, then we add to the next one. So 2 and 1, nope, we just keep on with the 2. And so same idea here, 2 1s come together to form a 2, a 2 and a 1, that's not the same. So the 2 continues on, 2 and a 1, not the same. So the 2 continues on, 2 and a 2, and so this becomes a 3. And so that's the Strahler method. Over here, the Shreve. What we have is when we have two streams coming together, what we do is we add the value. So 1 and 1, 1 plus 1 is 2. 2 plus 1 is 3. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 3 is 7. So now we go to the geoprocessing tool, different ways we can do it. Of course, all we have to do is change the method down here. So we go to our previous example here just south of Speedway and the Strahler method over here on the left. And so stream order, we see the number of values is lower. That makes sense. You kind of see how it's produces, in this case, the same stream system. In this case, produced a value of 3. In terms of the pour point, where over here, the outflows looks like a value of 7. So you can see the same stream network, how one has a value of 3, or the other one has a value of 7 in terms of the stream order. So then in terms of the output over here, we can see a large number of values. And so let's go ahead and let's zoom in. let's zoom into the confluence here and try to see if this stuff in reality plays itself out. And so what I did was I clicked on this particular pixel right here, which represents the flow coming this direction. So this particular pixel had a value of 2, and this one right there had a value of 2. And so that means 2 and 2, when they come together, when we have like stream order numbers coming together, that means we're going to be down here then a pixel value of 3. Meanwhile, using the other method, here we have the stream order was shown as being a pixel value of 5. And this one over here is a pixel value of 3. And so this particular stream is stream order 3. This one is stream order 5. Using the Shreve method, 3 plus 5 equals 8. And so now we have this particular grid here. That's now we have our stream network in which we have also added to that stream ordering. So we've given those streams not only a location, which we can identify them on a map, but we added to them some information. In this case, the stream order, providing a little bit of an understanding as far as the hierarchical nature of a stream network. So let's take this raster grid and let's convert it to a polyline feature. And so we can do that in the stream to feature tool, where it converts a raster representing a linear network to features representing the linear network. So that's exactly what we're trying to do here. So in this case, I'm using the Strahler order. In this particular example, our input flow is the most recent flow direction that we have. The output, I'm just calling it stream order 1, and notice the .shp because now we're moving from raster to vector. So we're going to create a shapefile. To simplify polylines, this particular option here, I tend to just go ahead and check it on. It just, I like things to be simple, but if you're doing research, if you're doing something in which I guess it has a purpose or a value beyond just clicking here, clicking there for an assignment, then you might want to look into this a little bit more. But go ahead and I clicked run, and here's our result. Now we have something which we can see a little bit more understanding. And so yes, this does look more like a stream network than what we produced beforehand with our flow accumulation grid. And so what we can do is we can then look at the stream order attribute table. So the stream order attribute table, we got the various information. So we got 103 different lines. So they got their ID here. We got the whole from node to node, which we talked about way back when. But then we have this grid code. What is the grid code? And so the grid code, essentially what it does is it carries over that stream order number. And so what that does is that it has a value that we don't see here. All the lines are essentially the same color. But what we can do is we can then change the symbology. And so we can say that change the symbology based on the grid code. So we can change the symbology based on the grid code. And so then we can then change the stream order. And so we can then change the symbology to unique values based off of the grid code. And then we can then from there change, let's say number 1 will make yellow, number 2 will make orange, number 3, stream order 3 will make red, and so on. And in sum, what we have is we have our Marion County DEM, in this case using the filled DEM with our higher elevation here than the original. And then we also have our stream networks, in which I've naturally covered them blue. And so we can see how they very much fit right in with that DEM. And we can see the general flows down here towards the southern edge of the county.